Hi, welcome to another tutorial. This one's a continuation of Timer1 high and low registers and capture, how to measure an incoming pulse. You can measure it using the Timer1 high and low or the capture. The capture register is going to update on the next incoming pulse after the first one you measured. So I'll just give you a quick demo of what's going on. That's the scope. I've got a 1 second per division, so my pulse going into the board's just over 2 seconds long, and you'll see the LEDs flashing away there. So what you can see is the Timer 1 low register is overflowing, and that's no use to anyone. You need to have the timer set up so that the time is slower than the incoming pulse you want to measure. But I'm just illustrating the Timer 1 low register, and as I said in the previous video, as the Timer 1 low register gets up to 255, it overflows and puts 1 into the next high register. So while that's counting, I've actually slowed everything down using the pre-scalers and taken out the 20 meg crystal, put a 4 meg in. I've got a pre-scaler on at the moment. I'll show you the code in a minute. I've got a pre-scaler for Timer 1 configuration set at B5, which is like a 1 to 8 pre-scaler. What I'll do, I'll remove that pre-scaler. So 85. Program. So I'm using the PIC 16F887. As I say, 4 meg crystal. I'm just configuring the pre-scaler, taking out the pre-scaler. I'll turn my signal back on. So now all of a sudden, with no pre-scaler, the counter's running too fast for you to see it. So obviously now it'd be difficult to understand what's going on here. This is the Timer low register. So what I'll do now is introduce the Timer H as well. Bear with me for a second. Right, and program that again. So as I say, the timer needs to be slower than the pulse that's coming in. Otherwise the counter's just going to roll over and not give you any sensible readings. Right, so now we've got Timer 1, excuse me, Timer 1 low and Timer 1 high registers. So that'll give you a count of 65,000, is it 535, which is 16 bits. So now all of a sudden you see the first counter's overflowing but it's updating the second register, and now we've got bigger numbers to deal with. So now we can increase our frequency going in. It was a couple of seconds. Right. Change that to, it's now 2 Hertz. So looking at the scope, I'll bring this out a bit. So it's not calibrated. I mean, this the counter time is not calibrated or anything. So we've got a pulse every 250 milliseconds roughly. And you'll remember I said, so Timer 1 gives you an instant reading. The capture is only going to update on the next rising edge or falling edge, depending on how you've got it configured. So that's like a 2 Hertz signal, a 250 millisecond pulse, giving us 294. If I speed it up to like 3 Hertz, so let's go to 4 Hertz. You can see the timer's only counting, it's reaching 150 before it's resetting. The captures, it's got a big clock cycles, it's slightly different, and this is updating on the next rising edge. So that's the timer, that's the capture. As I said, I'll show the code in a minute. So if I turn that up to like 10 Hertz, And it's obviously, that's 20 Hz, which is obviously too quick for the LCD display. But what you could then start doing if you've got a fast pulse is counting every like 4th edge or every 16th rising edge, something like that. So I've just slowed everything down just with demonstration purposes. Well, slow it back down to, so that's 2 Hz. Put it back to 1. If you want to measure a slow signal, so you see the LED turning on in the corner there, just down here. That's my incoming pulse. Port RC2 is configured as an input, and the time, as soon as that goes high, the timer turns on. We're measuring it and also capturing it, and you'll see the capture information's updated, as I say, to reiterate on the next rising edge. Hopefully you understand that. So coming across to the screen, there's a micro C for those of you who haven't been looking at my recent videos. Hopefully you can see all of this. Well, if I start at the beginning, well, this is various integers for the numbers, and jars for the converting the numbers to strings, so I can display them on the LCD. I'm only, this demo is only using time and time 2. Set up your LCD like that. This is an easy pick version 7, so that's the configuration for the 887. That's my configuration. So CCP1 configuration is CON, CCP1 CON. CCP1 is on RC2, so that's the capture mode every rising edge. It's actually 4. I've got the gate inverted. Timer1 configuration 85. I previously had it on B5, which is 1 to 8 prescaler. That was to slow it down so you could see it. IntCon, so interrupt configuration C0. That's global interrupts, peripheral interrupts. Option reg. Peripheral interrupt enable, and that's peripheral interrupt request. No comparators disabled. All ports digital. There's my input for port A. So that's time. 10 timers off. Emptying the registers. Just a bit for when my LCD starts up. Right. So this is what I've got in the loop. Do so. Enabling the capture compare if RC2 bit, so if RC2 underscore bit, so if RC2 becomes 1, then timer 1 on and capture 1 is configured, and these are the bits I was showing you earlier. So that's my first timer register. I was showing you just the count of 256 or 255, depending if you include 0 as a number. Timer 1L, then I introduced timer 1H register. So every time that counts up to 256, you get 1 in here. So if you're using this in the display, multiply by 256, because every 1 is 256. Hopefully that makes sense. On the next rising edge, the capture compare is updated. Once that's happened, I'm turning the timer off, stopping the capture, clearing the capture, otherwise you get a flag. And these are int to string, so displaying the integers to string so I can display them on the LCD. So time 1 is 16 bits, so it's word to string for time and time 2. LCD out, text 2, and then after each capture I'm clearing the register. So when RC2 bit goes 0, when the signal's off, I'm emptying the registers. So next time it goes high, I'm starting again, and that's the while 1 loop, and that's me done. Hopefully that made sense. You can capture a signal like that.